Okay, we're going to go ahead and finish up some ideas that we started on Wednesday before the bell rang, and we'll just go back to looking at page in your book. That page in your book, let me look it up here real quick. We are in chapter 12, and we are looking at a chart or table that you should have some information on in front of you. If you don't, you will need to get a book. So I'll wait a second and get a book. And you need to open up to a table of results that we can look at on page 561. So here's the table on page 561. And what we're doing is we're looking at how the initial rate, the initial rate, I rate is over here to the right, and it's 1.35 to the minus 7th for experiment 1, and so on, down to 5.4 times 10 to the minus 7th for experiment 3. We have different experiments with different concentrations. We initially looked at finding orders. We said an order of 0 is where there's no change in the rate. So if that was the case in experiment 1 and experiment 2, then the rate would be the same even though there's a change in concentration. And that's not the case in these 3 experiments. A rate of 1 is called a direct relationship. When the concentration of one of the reactants would double, say, then the rate would double. Or if the rate would be cut in half, then we know the concentration was cut in half. So that's called an order of 1. Now going in our rate law. An order of 2 it was called a square relationship, where if the concentration doubles, then the rate actually goes up 4 times. So that's a square relationship. And in physics, there's some different square relationships you had to do, like gravitational pull and the radius. It was squared between 2 large objects. That would be the same here. There's a square relationship that's involved. So we're going to go ahead and take a look at example experiment 1 and experiment 2 again, just to refresh your memory. What happens in experiment 1 and 2, NO2 is doubled. So we're going to go ahead and write that down and show that how you would find it if you didn't know how to find it. So we'd go experiment 2 divided by experiment 1, and we would look at their concentration. So it would be 0.010 divided by 0.005 molarity. That's their concentrations, experiments 1 and 2. And we can find that we get a value of 2 out. Okay, so it's two times as great in between those 2 experiments. If we do the same for the rate, we do the same thing. Experiment 2 over experiment 1. When we look at those results, we would see 2.7 times 10 to the minus 7 over 1.35 times 10 to the minus 7. When we would do that, we'd also get a value of 2 out. So that's an order of 1. Okay, so I'll write that down here. NO2 minus order 1. Okay, so it's order of 1. That will go in our value for N in our rate law. Okay, we'll go ahead and do that later. We're going to switch up things. We're going to look at experiment 2 and experiment 3. When we look at that, the rate for NO2 stays constant, but the concentration for rate for NO2 is constant, but the concentration of NH4 will go up between 2 and 3. So we're going to go ahead and do the same thing. We're going to erase what we had 2 and 1 in their concentrations. And use the same format. We'll see what our rates Comparison would be with the concentration change. So we'll go ahead and look at experiment 3 divided by experiment 2. So that would be 0.20 molarity for experiment 3. Divided by 0.10, and we get a 2 out again. And we do the same thing with rate, 3 to 2, when we compare that ratio, 5.4 times 10 to the minus 7. In experiment 2, 2.7 times 10 to the minus 7. And that's also 2. Alright? So then, what we have for NH4, that's also order of 1. So, what we need to do is we need to write the rate law. Okay, now I've already done this for you, and I will explain it. There is a calculation that's done, and I'll explain that as well. So, in this first box would be how we would come up with plugging in our orders. Rate is equal to K, constant, times the concentration of NH4 plus to an order of N, times, because if we have 2 reactants, we'll have to multiply those 2 in the rate law, times NO2 minus to order of N. Again, we're going to put the orders in there when we need to. Alright? So down below, we have our experimental rate law for the one we just did. Now, if N is 1, we don't have to put an exponent of 1. Okay? So we'll just write it like it is here. Now, if it was 0, it wouldn't even show up in our rate law. We wouldn't even include the concentration in our rate law. Okay? If we're wanting to solve for K, we have every variable. So what I've done here is I've looked at what we call experiment 3. If you look at experiment 3, the rate is 5.4 times 10 to the minus 7th moles over liters times seconds. I'm going to write it in that form from now on. I want to show every unit. That equals K times the concentration of NH4 in experiment 3, and it's 0.2. And then I also put in the concentration of NO2 from that same experiment, and it's 0.01. So then what I want to do, on this next slide, I will show you the setup to solve for K. So when we solve for K, we just divide both sides by their molarity. That isolates K. So what we'll do is show the units for molarity as moles over liters for the concentrations as well. So when we do that, we're going to go ahead, and that's this first box of what we're doing. We take 5.4 to the minus 7th molarity times seconds divided by the 2 concentrations to get K. Okay, when we do that, we get a certain value out. I'll share with you here in a second. The bottom box represents another experiment. So the top box is experiment 3. This bottom box is experiment. If you look at your values, it's going to match up with experiment number 1. So again, we would plug the numbers in the same way and switch them around same way. And if we would go ahead and look at the label of our final answer and its constant, it's going to be the same. Alright? So there is our example. And if we would do the calculation for that, we would get 2.7 times 10 to the minus fifth for both of these. Okay? The units that we would end up with would be the following. We would go ahead and have it read as liters per mole times seconds. Okay? Because what happens is a liter is in a denominator that's dividing, so that will be up above, be actually L divided by moles times seconds, and that would be the units for that example. Okay, now that we've done that, and you know how to use the rate law to find the constant and look at finding orders, we're going to do one that's a little different. It's on page 562. You should see a chart that it's at the bottom that looks like the one I have here with bromate, bromide, and hydrogen ions. Okay? So I have the concentrations and the rates. So go ahead and we're going to look at experiment 1 and 2. The only thing that's different is bromate. And bromate doubles. Right, here's doubles. So it's 2 times. And you can kind of see without plugging the numbers in, which I'm not going to do this time. When we look at those rates here for 1 and 2, when you take 1.6 to the minus third divided by 8, it also doubles. So if that's the case, then BRO3 is an order of 1. Right? So then the next scenario we can look at would be experiment 2 and 3. Bromide doubles. So then what happens to the rate there? It also doubles. Okay? So 3.2 to the minus third divided by 1.6 to the minus third is 2 times. So guess what? We get another order of 1. So we'll go to the last one. This will be a little different. What we want to do is find 2 experiments where bromate and bromide are constant, their concentration don't change, and then hydrogen actually doubles. Let's see which one. Oh, that would be 1 and 4. So if we look at experiments 1 and 4, we're going to have to take a look at H plus doubling. Right, so when H plus doubles, which it's doing, we're going to go ahead and show what happens to the rate. So we'll do like we did before. Experiment 4 and experiment 1. When we compare those two and their rates, then we're going to take 3.2 times 10 to the minus third. And we're going to divide by 8 times 10 to the minus fourth. When we do that, we're going to get a number that is equal to 4. So the rate goes up 4 times when we look at the concentration change. I'll go ahead and show this. Between those 2 variables, or those 2 rates, that's a doubling. So H2 doubles. So over here we put experiment 4, experiment 1. When you look at those, that would be 0.2 divided by 0.1. And that's 2. So anytime you come up with a concentration that doubles, for example, and the rate will go up 4 times, that is a square relationship. So guess what? Got a lot of stuff going on here, but H plus would be an order of 2. So I don't have room underneath, but H plus is an order of 2. I'll put it up above here. Okay? So how does that go in your rate law expression? I'll go ahead and show that. So, again, rate is going to equal K. We're going to put our orders in. First one we're going to do is BRO3. We're going to multiply by BR. And then we get this order 2, it's H plus. Now we're going to go ahead and square that. Because in order 2, we can go ahead and put in the square, and that would represent an order 2. So then we would go through the same thing to solve for the constant. For example, we can take experiment 1. So we'll do this real quick. We'll go K is equal to the rate divided by the different concentrations. Okay? So it'll be BrO3, Br, and H plus. So we'll pick at experiment 1, 8 to the minus 4th. That would be moles over liters times seconds per second. Okay? And then we would put in our different concentrations. So we put in, this will be real easy, 0.1 times 0.1 and 0.1 squared. Alright? So then I need to make sure I put my units in here to kind of show you how that works. So I'll put each one of these moles per liter. Okay? So the 1 mole per liter cancels out. And what we're going to end up with when we do this is molarity times molarity. So the liters would be squared on bottom. The moles would be squared on bottom. So then our actual units, when we come up with an answer, we'll do the units first, would be liters squared over moles squared times seconds. Right? That's what we, nope, I take that back. I apologize, that would be, when we square the molarity there, that would make our values not be that way. I apologize again. So when we square molarity, so that actually would be molarity squared times moles would be molarity cubed, and liters is also cubed. So that would be our units for K. Okay, then after we plug all the numbers in, our answer is 8. Right? So it would be 8 liters cubed divided by moles cubed times seconds. If you look at the bottom of page 563, they show a lot of that work, and then they give the answer. Same exact as what we came up with. Okay? So there will be an assignment for you to work on that the sub will have. And then on Friday, you will go down to the Media Center to work on your lab results for Beer's Law.